Caio Lewenkopf from Universidade Federal Luminescence, Brazil. And he will talk about backscattering induced by disorder in the topological insulator phase of graphene. So please.
Thank you. Well, first I'd like to thank the opportunity to speak here. I have been working in 2D materials for a while, but not with spin. Well, as Stefan would say, my spin is a factor 2, but this is a different work. And I try to convince you that there is some interesting stuff in this topological phase or the backscattering suppression. Okay, so this is my collaborator. He was a former postdoc in my group. Now he got a position. So there are still few positions in Brazil despite the crisis. And this is the outline of my talk. I'll just repeat some of the we are going back to tutorial number 2. So repeat some of the stuff that Stefan presented just to refresh our minds, because we had all this TMDs and now people are probably tired. And I'll explain briefly, the main ideas of the quantum spin Hall, then I'll do some engineering of the spin orbit coupling, and then I'll go again through the no local resistance. And then this is the main topic of my talk. Okay, so this we have seen just around 9 a.m. And so this paper here was very influential because it was one of the papers that contributed to the starting of topological, the whole subject of topological insulators. So the thing is, they studied the quantum spin Hall in graphene. And for that purpose, they used the type binding that we know, and they added some, by hand, some some spin orbit term, and then they got this nice dispersion relation here, and by basically the spin orbit will open a gap, and then they'll study this edge bulk duality and show that there are symmetry protected topological states at the edges, and they have some spin texture. So they used, for the purpose of their calculation, they use a very large spin orbit coupling. And we heard also here today that, this was very unrealistic, and I learned that this year people actually measure it. So in order to do this beautiful physics, people went to other systems, and they were shown here. Quantum wells and mercury telluride quantum wells, etc., and the phenomenon was observed. So if we want to do this in graphene, then there were some ideas put forward many years ago, then 10 years ago, by engineering the spin orbit coupling by chemisorbed add atoms, and they will create some lattice distortion, and there were some back of the envelope estimates for how large this spin orbit term will be, and over the years we got lots of very interesting and detailed calculation, and we actually have realistic studies nowadays for different add atoms, and we know how to model that in a realistic, more realistic fashion. Okay, so the idea is then to have graphene and then to randomly distribute the add atoms. And so basically, if you know the effective spin orbit term here, how it modifies locally your band structure, your let's say matrix elements, and you know the concentration, then you can play all sorts of games and explore this kind of physics. And basically, this motivated also people to do some experiments, and some of them were very successful and reported a large non-local resistance due to this decoration of spin atoms, of add atoms, and this was actually interpreted as the spin current, and then you have a spin Hall effect due to this spin orbit engineered system. And well, this motivated lots of theoretical studies, but still people that were looking for the topological gap experimentally they failed, and there were many reports in the literature that in this way you don't advance too much. Okay, so the question is why, right? And from the theoretical point of view, we also saw that. So there is a nice simple model for the spin-orbit coupling in graphene by adding atoms. And this is this work that was mentioned several times here by Weeks. And it's very simple. That's one of the advantages. And you can map this Kane-Meillet model. And well, basically, for very heavy elements, you get a gigantic, let's say, effect. And you can actually think about what happens if you change the concentration and, you know, this stuff. So you have the spin orbit gap. Okay, so at that point, we have some model, and we can play all sorts of games. And this is also something that Stefan mentioned. And most of these experiments that have been done, they use actually this geometry of a Hall bar. And then if we go back to Büttiker, who generalized this Landauer formula for multiprobe, then you have a very simple expression here for the current that flows through your terminals, and basically as a function of the different voltages. And actually what you have to do is to compute, well, it's zero temperature if you want. So you have to compute the transmission coefficients. It's a quantum mechanical calculation through the system. And depending on the size of the system, this can be very demanding. But in principle, this is something that your computer can do for you. So if you have a model, your type binding, you can actually access systems of easily millions of atoms and sites, sorry. Well, basically, then you do some circuitry, Kirchhoff law, et cetera, and then depending on how you make your experimental setup, for instance, this is the most interesting one, you flash your current through this device, through this terminal here, then you can measure here, and then by conservation of current, you know what the currents are. And actually, this non-local experiment, you measure the difference in voltage, this red one. And if you have a quantized mode, then this is basically, this is one of the single mode, you have this answer. Okay, so this has been explored. So in principle, you need to do that. And so Leandro, his former postdoc, he developed a very smart algorithm to compute this transmission using a method that we like, which is recursive Green's function. And it's a smart slicing of your system, so you can do any kind of geometry, et cetera, and it's well, it's competitive with other methods I mean, numerically competitive with other methods that are on the market. And so he was very proud of this. And basically, we can compute, for instance, by changing the concentration of add atoms in a geometry like a Hall bar geometry like that. You put some other additional disorder. Then as you move you increase the concentration. You start with very little concentration up to 10. Then you see that density of states in this guy here, and it changes a little bit. And at some point, you see that there are some developed edge states. And you can compute also the local current. So if you inject through this lead here, then at low concentrations, then you have things all over the place. And if you start increasing the concentration of the add atoms, they go slowly to the border. Eventually, everything is an edge state. And there are different regimes in that, and this is also beautifully discussed in this paper. So one has to understand, to get some feeling about this non-local resistance, and there are different terms that contribute. Yeah?
It's related to an earlier question I had for some other speaker, where you had the edge states right at the entrance of the reservoir. So what happens?
This is question number 4. And
Four.
what was it? So if you hold a little bit, I have a better one for you, and I can explain to you what's going on. So this is this Hall bar. When we consider two-terminal geometry, then I have a very neat transparency of figure to discuss with you. So, and then okay, so the thing is that you have within the gap, no, the topological gap, you have this quantized resistance, and then well, actually here we put a strong scalar disorder. This is Anderson model, and it's really protected against disorder. And as soon as you increase the Fermi energy or the chemical potential, then behaves like lots of localized states, if you wish. Good. So it's not absurd. What can go wrong? And well, we have this discussion today. Stefan defends this picture of clusters. And as you put more and more, let's say, add atoms, they tend to cluster and the effect goes away. And then it was argued by Iris that actually the reduction of the DFT calculation by weeks to a tight binding is not, well, there are extra terms that if you take into account, all this goes away. You can also add, there are charge puddles, and if you have fluctuations of the chemical potential would exceed the gap, then also the effect is not there because you have percolating around your system normal material. And despite all these criticisms, well, you can also argue that eventually you can generate this effect by proximity or other mechanisms. You don't need to rely on this particular add atom construction. And we actually set up a different point of view. You want to understand that by the effect by breaking the topological protection by considering the presence of magnetic impurities. So, and this connects to other things that have been discussed. And basically, the idea is that we like to consider the formation of local magnetic moments due to for instance, vacancies, add atoms, or even edges. And so we had done some work in that front. We studied the effect of vacancies to form a Kondo effect, and this was a work by Vladimir, who is sitting here 5 years ago, and also vacancies or add atoms for spin relaxation, and this is also Vladimir, who is talking about this subject on Friday. So if you are interested, you should ask him. And my stuff here is more edge magnetization. And well, we know that the borders, the edges of graphene, depending on how you cut them, they might show some magnetic, local magnetic moments. Well, this was the first work in this was in '96, so we were already thinking about that. Graphene nanoribbons many years before graphene was actually made. And it was a big step forward by this paper by Stephen Louis and Marvin Cohen, who actually did some DFT calculations in 2006. And later there was also the idea of having Caio edges in connection to experiments. And this was a nice paper by Yaziev here, who collaborated with these guys. And we also consider some stuff in Caio edges. So what is the model and what are we interested? So first we consider local moments due to vacancies. And then what happens is that if you have a vacancy in the simple-minded model, then you create a localized state. And if you have a localized state, in order to populate it, you have to pay a charging energy. And actually you can map this simple model of graphene plus this localized state and its coupling to the standard single impurity Anderson model, which is the basis of Kondo and local magnetization different materials. So alternatively, you can also consider local moments due to an add atom, and it plays the same role. So the add atom, you need some energy to charge it, to populate with more electrons, and actually this has even a simpler relation to the Anderson model. So vacancies or add atoms will look like that. Inspired by this, actually there was a PRL in early this year that Paulini and group, and they actually considered the Kane-Meillet model plus the Hubbard interaction. And well, this is an idea of getting the edge of the system well described. And actually this is done in the spirit of Hubbard mean field, which is inspired in these early works by Marvin Cohen and Stephen Louis. And this is the effective Hamiltonian retreat. So the magnetization could, like it's not perpendicular, so you can flip the spin of the electron by this term. And they did some calculation which was, well, they consider a large system, and then they put the contacts, and like it's not really what we wanted to do. And so we actually run the code, which is this RGF, this method recursive Green's function with interactions with the mean field. And we heard something similar by Branislav Nikolic today. And there is an old paper by him describing this. We have a similar code running for us, and it's nice because it can handle very large systems as well. Okay, so in the sense we can treat the system in a mean field. You can compute this stuff, the occupations, local occupations, compute the local currents, everything you like. And so this is our working tool. So vacancy disordering, you extract one guy here, and then what happens is that for the purpose of being faster, we consider just the vacancy at one of the sides. So the other, I mean, this, if you think about quantum spin Hall, then this edge is preserved, so it's quantized all the way, and this guy can be destroyed. And what happens is that this kind of model, it's always like that. You have, if you're outside the gap, or you are in the gap, but outside the region where it magnetizes, then you have a perfect transmission both sides. And then it's only, there is a resonance here, which affects the transmission, and then there is something which is not easy to explain, and then it goes back to normal. So, and then if you look at these points that I draw here, A, B, and C, and this is the picture Egis probably would like to discuss. So basically A is a situation where you have this quantum spill Hall, and if you flash the electrons from this side with the right spin, they flow, and as soon as you get into the region where it's influenced, the point B, where the region where you start having, oops, sorry, this backscattering. Yeah. Oh. Uh-oh. Yeah. Okay. Bad coordination. Sorry for that. Yeah. I'll be here. Yeah. Yeah. Oh no. It takes a while to load. That's the bad thing. Sorry. Yeah, okay, my last try. So this is the point B. This is where the effect is most prominent. So the B is where actually the thing is that you have this state that there is a backscattering, and the electrons won't flow from this part. And coming, well, so for your question, the idea is that, for instance, here, if you're in the quantum spin Hall phase, then this reminds you that this is the Landauer-Büttiker scenario. So basically, you have currents flowing from both reservoirs, and they cancel each other until you get to close to the Fermi energy, where you have this small bias, and then one will win against the other. So the thing is that in this sense, you send the unpolarized current through this side, and once it gets here to the region where you have this quantum spin Hall, the electrons realize they cannot really propagate. For instance, if you have one spin polarization, it cannot propagate through this side. So they have to go here. And so there is a region which is short, and all the electrons will flow through one of the sides. So the thing is that we played a lot of different games modeling this interface. And what happens is that it doesn't really matter what you do. In this regime, you always get a quantization. There is no backscattering in this sense. So we tried a ramp, we tried different contacts, we doped, undoped. And so this is the same picture as Stefan. So it's a feature of this Landau-Büttiker kind of stuff. So it's 0? No, they didn't.
Okay.
They didn't start.
Like you said that you tried different contacts.
Yeah.
Also, like in terms that you change the lattice to square lattice.
Yeah.
Okay, but it breaks the symmetry, right?
Yeah. The thing is, if you have, this is a funny thing, because if you have a square lattice, or you have lots of linear chains, or there are different models. Then if you are not in this quantum spin Hall phase, then the pattern of interference really, it's very different. You have some geometry which is not just a graphene nanoarray. Why? Because basically the impedance changes, and let's say the matching of the electrons that come from your lead to your main system, they change. So as soon as you get here, you actually don't get this effect. But even if I would get that, so I'm reporting here just two terminal, but we know how to do a Hall bar. And in a Hall bar, you can actually play games so that you eliminate the contact resistance. So this is not our main concern. This was our motivation to do the Hall bar, because then you eliminate the contact resistance. All these features, they are more prominent in, So if you get both, in any case, it's sensitive to the density of states of the leads. That's for sure. But on the specifics, yeah. Oh, that's very technical. Well, okay.
Thank you very much, Caio. So blue and red is spin up, spin down.
Yeah.
So the red figure is I guess it's easy to understand that you
Mhm.
have a vacancy, so you're treating, I mean, a kind of magnetic dependent scatter, right? Which I don't know if there is a kind, this dark zone is increasing, so does that mean that there are more and more vacancies, and then you want to see at which time you completely shortcut, you completely disrupt the topological state, right, for the down spin? But what is the blue? So I don't understand what happens on the
No, the
blue
thing,
curves.
yeah, I'm sorry. So this is a single vacancy, right? So this is the extent of this localized state, okay? So the localized state is localized, but it's not in a, it occupies some region. So the idea is that here, what happens is that you actually flip the spin, and then you propagate in this direction. So actually I should add here that basically I inject here the spin, and basically it understands that it will flip here and then it go back. So that's the idea. So this guy is responsible for flipping the spin. And well, these are some details of the model. And we can actually understand this map this into there was a nice paper here that we could map this into a very simple model by projecting our model Hamiltonian to 2D with effective local moment. And actually we can extract parameters like this delta, this gamma that these guys developed for us, very simple model for our model. And we realized that actually, no matter what you do, if you have vacancies, and backscattering is suppressed only in very narrow windows, so it doesn't explain the phenomena. And that's the point. So no matter what we do. So then we need another mechanism for these local induced magnetic moments, and this is basically the zigzag or Caio edges. And we saw, I think yesterday, that if you really work hard and try to produce really good edges, they're never incredibly regular. and then most normal situation you find something that that has some zigzags or some armchairs, and then Cairo and mixed. And so this is a realistic thing for, I mean, if you have good borders, you know, like good edges. And so this is what we do. So we started modeling a very simple thing. We preserved one of the edge. We cut a wedge here. So this is armchair, and there is a zigzag. And we wanted to see, we know that zigzag has magnetic edges. And we wanted to see how many of these zigzag links you need to have the effect. And in this particular geometry, you see that with 3 zigzags, there's a perfect guy here, and then you actually reach the region where there is no gap anymore, and then it's normal. If you have 5, then it starts moving here. But as soon as you get 6 or 7, then basically you entirely destroy one of these edge modes, as in the vacancy, but you destroyed all over the whole topological gap, and that's important. So you destroy this guy. So that's the idea. And then, well, this is one of the figures that Agus likes. And then we did something a little bit more, let's say, realistic. Well, we sorted like many of these realizations, picking up at random some of the sites. And if you are sufficiently long, then eventually you hit a situation where you have 6 in a row. And that's enough, because then you have a local magnetization. This is in arbitrary units, the magnetization. And this is enough to suppress the topological, the quantum spin Hall in this effect. So in essence, this is the summary of what we did. So I'm not defending too much the model where we start with the type binding for the quantum spin Hall, but I'm actually more interested in understanding what are the mechanisms to really suppress it. And as soon as you don't have perfect edges, then it's very unlikely that you see the effect. So I guess that the vacancy is not it's a nice paper, but it's not the mechanism that will save you. This is the mechanism that will save you. And yeah, sure. Huh? Since you like this picture, okay.
Now, in the previous picture you showed, you had the system coupled to leads.
Yeah.
So then there's some broadening, which is the coupling to the leads. Can you actually see? But I didn't notice whether, you know, going up, you know, the edge was a bit wider or not compared to the other. And then here, compared to the horizontal one, right? Because there's no coupling on, say, going that way.
I see. I cut the thing because it's boring. So in our model, you see these dark regions here. This is where I put my let's say, my add atoms. And here, if you have really good eyes, you see that there is a perfect lead connected to it.
Okay.
So, and then I decide, well, I'm not going to make it very large. And the idea is that I inject the current from one side and see what's going on. So the current is initially unpolarized. And so what happens is that I inject the current unpolarized from this side. And the typical pattern that I find is that the spin up, for instance, will flow in this direction, and the spin down will flow in this direction. I preserve this edge perfect, so it will flow and happily until the end, right? And the spin up will hit this region where it's magnetized. It'll flip the spin, and then you have a back current here of you know, so that's the idea. So you flip the spin and you flow the other way. So that's
right. But I guess my question is, why is it that the edge states around the vertical line? Yeah, it's a bit, you know, narrower. Narrower as compared to the one on the horizontal. But say, let's look at the red one.
This down here.
Yeah, down there. Yeah, and then
so you're saying that this one is
a bit wider, it seems, no?
Yeah. No,
I would expect the other way, because there's coupling on this side to the leads.
Yeah, but you see, it's hard to, I don't have a good physical picture, but these two situations are different. Because once you you hit this part here, then first of all, you are unpolarized. And second, you flow to a region with a higher density of states. And so it's hard to map these two guys. So it will be funny if there will be an order of magnitude difference. But if you have something which varies by a factor of 2, it's really hard to try to figure out some explanation for that. So remind you that I have graphene, but heavily doped to simulate the metal, and then it flows to this region here. And then something happens. The charge have to rearrange, and they do. So that's it. Well, the conclusions are this slide, so I leave it here.
So we have one question. Okay, so thank you. Okay, so we already have some questions.
So just to complement Carlos' question, can you go back to that figure?
That the previous one. Let's see if I manage. Okay.
Yeah. So